Done. Sine of 75 degrees is just sine of 30 degrees plus sine of 45 degrees.
Stop! That is the cardinal sin of trigonometry.
What? It works for linear functions. Why not sine?
Because sine isn't linear, let's look at a simpler example. 30 degrees plus 30 degrees. Sine of 30 degrees is exactly 0.5. If sine was linear, then sine of 60 degrees would be 0.5 plus 0.5, which is 1. But sine of 60 degrees is actually only about 0.866.
Oh, the curve levels off, so the steps get smaller as we go further right.
To prove this formula, we can use a geometric construction. Let's set OP equals 1. Our goal is to find the length PQ.
That looks like a challenge. How do we start?
We build a scaffold. Drop PR perpendicular to OY. Then drop R to S on the x-axis, and draw RT perpendicular to PQ. In right triangle ORS, RS is OR sine of alpha. And in triangle OPR, since OP equals 1, OR is simply cosine of theta. Now for PT. Notice that angle TPR equals alpha due to the perpendicularity. In triangle PRT, PT equals PR cosine alpha equals sine beta cosine alpha. Finally, adding RS and PT gives us the formula we wanted.
What about the formula for sine subtraction?
We can deduce it by replacing beta with negative beta.
And since cosine is an even function and sine is odd, so for sine, subtraction stays subtraction. The sign matches.
But for cosine, the sign is flipped. It's contrary. Imagine 30, 45, and 60 degrees are like Lego bricks.
Okay, I have a 30 brick and a 45 brick.
Snap them together to get 75. Or compare them to find 15. But remember, trig functions don't work like bricks. You must use the addition and subtraction formulae. How do we find the exact value of sine of 15 degrees? Let's use angles we know.
Since $15 equals 45 minus 30, we can use the sine subtraction formula.
Expanding the expression gives us products of sines and cosines.
Now, we look at our table for the exact values of 30 degrees and 45 degrees.
Substitute the fractions into our expression carefully.
Multiply the terms to get our answer.
There it is, the exact value of sin of 15 degrees in radical form.
Now, let's find the exact value of tan of 105 degrees.
We can use the tangent sum formula by splitting 105 degrees into 60 degrees and 45 degrees. Substituting our known values, tan of 60 degrees equals root 3 and tan of 45 degrees equals 1.
Now we have a radical expression. To simplify this, we must rationalize the denominator. We multiply both the numerator and denominator by the conjugate, 1 plus root 3.
Expanding the numerator and simplifying the denominator gives us...
Finally, simplifying the fraction leads to our exact result.
Wait, the result is negative, is that correct?
Yes, 105 degrees is in the second quadrant, where tangent is negative.
Oh, right. It's between 90 degrees and 180 degrees. That makes perfect sense.
Let's solve this equation using the expansion formula.
The variable x is trapped inside the sine function. How can we isolate it?
We can use the compound angle formula to expand the left side.
Right. Now we substitute the exact values for cosine and sine of pi over 3.
Next, subtract 1/2 sin x from both sides to group the sine terms.
Dividing both sides by cosine x and 3/2 turns this into a tangent equation.
Exactly. For x between 0 and 2 pi, we find our two solutions. Case 2. Compression.
4 terms? That looks complicated.
Look closer. It's the sin A cos B plus cosine A sin B pattern. We use the addition formula in reverse. Don't forget to shift the domain for the new argument. Now just subtract the shift to find x. Compression turns a long equation into a simple one. Let's derive the double angle formula for sine. We simply use sine of a plus a.
That makes sense. How about the cosine version?
For cosine, we follow the same logic, but we can derive 3 useful forms.
Wait, why are there 3 different versions?
By using sine squared a plus cosine squared a equals 1, we can express it using only sine or only cosine. These variations are helpful depending on whether you want to eliminate sine or cosine.
Is there a formula for tangent as well?
Absolutely. We use the tangent sum formula for its derivation. And those are the three main double angle formulae you'll use. Today, we'll prove this trigonometric identity using double angle formulas.
We want to cancel the 1 in the numerator. Which cosine 2a formula should we use?
The third one, 1 minus 1 minus 2 sine squared a, will eliminate the constant term perfectly.
Let's start with the left-hand side.
Now substitute the chosen formulas for cosine 2a and sine 2a.
Expanding the numerator. 1 minus 1 is 0, and negative 2 sine squared a becomes positive 2 sine squared a.
Great! Now we can cancel the common factor of 2 sine a from both terms.
And sine a over cosine a is exactly tan a. Proof complete.
The key is choosing the cos 2a version that simplifies your expression fastest.